Okay, great. Thanks very much for the opportunity to speak here, and thanks also to Professor Grellenberg for her very interesting talk. I'm going to talk today about lessons learned from modeling the cost evolution of 3 low-carbon energy technologies: solar photovoltaic or PV systems, nuclear fission power plants, and electric vehicle or EV chargers. And I wanted to begin today by discussing a few key ideas underlying this talk. The first of which is that how we measure technology improvement critically affects our ability to devise targeted innovation strategies. In other words, we can be a lot more specific in how we invest in improving existing or scaling new technologies if we have a better understanding of the historically successful avenues for technology improvement, and perhaps can even foresee limits along some of these avenues. Now, a common research question in this area is to consider the unit cost of a technology, either at 2 points in time or at 2 locations, and essentially ask, why are these costs different? Why have they come down over time? Why do they differ across locations? One may be interested in this because one is studying cost evolution of technologies over time. Or one may ask, why is the cost of a photovoltaic system that's shown here repeatedly different in one city as compared to another? Or if you're in a city like Hong Kong that is highly space constrained, you may be interested in shifting the deployment of solar PV increasingly from land to water, and you may be wondering which specific technology features drive cost differences between these 2 technologies. Now, one common way to aggregate technology costs is to think of the cost of a technology in some currency per unit as the sum of hardware costs and soft costs, where hardware costs are the costs of physical components and soft costs are the costs of deployment processes. Now, if we use this conceptual model to answer the research question I've posed here on the left, and study the changes in technology costs over time, we're going to get an answer that looks roughly like this. So we may associate changes in hardware costs over time with hardware improvements, with physical changes in technologies. And we may associate changes in soft costs, so the costs of processes and services, with process improvements. That's intuitively clear, it makes sense. However, it does gloss over a bit over the detail that these cost components are in reality determined by 2 different types of technology characteristics or features. And I'm going to call these, for the rest of the talk, hardware variables and soft variables, where the former represents features of physical components. So this could be material usage ratios per unit, material prices. And the latter, soft variables, represent features of deployment services or processes. So how long it takes an installation worker to deploy a certain component and how expensive the labor is that he or she delivers. Now, a crucial difference between these 2 types of variables is that innovations in hardware, so those that affect hardware variables, tend to affect both hardware costs and soft costs. So they have a sort of dual nature, and the very simple conceptual example you can think of is if you reduce the mass of a technology component, it not only reduces material costs, but it may also reduce the cost of lifting this component simply because the component is lighter. In contrast, if you innovate in this process, if you come up with a new way of lifting this component up, you're not changing the physical nature of this component. And so we can generally think of process innovations or soft innovations as affecting soft costs only. Now, when we use this, I would argue, somewhat improved model to come back to our bar chart here, we need to add a 3rd bar, which then accounts for the contribution of hardware improvements to soft cost change over time. And much of this talk today is going to be about trying to convince you that adding this third bar here is important for interpreting historical and also future estimated cost trends in low carbon energy technologies. These dependencies of soft costs on features of hardware, by the way, are a more general problem in clean energy development. So I give you a very simple example of a material usage ratio in one component earlier, and I'm going to give you more examples when I get into actual specific energy technologies. But just to give you a sense now, one could also think about component shapes, which affect how we may be able to stack component and how many units can be delivered in a truck. We can also think about component diversity, materials used, vendors involved, and what that means for managing a supply chain, and how it affects supply chain costs, which is also a process cost or a soft cost. So the point I'm really trying to get at here is that studying changes in high-level cost categories can mask underlying drivers of cost change. And I'm going to show that changes in soft costs can stem to a large degree from hardware innovations rather than from process innovations. While in contrast, soft variables, which are again features of deployment processes in this framework that I'm going to present today, tend to be less influential or even get worse, meaning increase costs over time. And so in the long run, particularly deep decarbonization will very likely need to leverage both avenues for innovation, so both reducing hardware and soft costs by innovating in pieces of hardware, but also explicitly focusing on processes and human interactions to target these soft variables more explicitly. But let me step back a little and ask why bother about soft costs in the context of climate change in the first place. Something that we know is that multiple low carbon technologies exhibit rising shares of soft costs. So for photovoltaics, again abbreviated here as PV or wind, that has to do with the success actually in reducing the costs of core energy conversion components such as photovoltaic modules and wind turbines, wind towers. So these are hardware components, and they have come down slightly faster as compared to soft costs, which increases the share of soft costs in total installed costs. For nuclear, in contrast, both hardware costs and soft costs have risen over time, but soft costs have risen slightly faster, leading to a higher share today as compared to earlier in time. Now, thinking about both these cost components is important if we consider the significant gaps between planned and required clean energy investment levels, required if we're trying to meet climate change mitigation targets, regardless of whether it's the 2C or the 1.5 degrees C goal, as well as broader sustainability targets as mentioned before by Professor Krellenberg. Thinking about soft cost reduction in a targeted way is also important, considering that the solar photovoltaics industry increasingly contributes to jobs creation. So here this is shown in yellow. That's a global study published by IRENA in 2020, and you can see that PV contributes quite substantially. So we don't want to think about soft cost reduction without being very careful about which technology features we're changing potentially in the future and what that means for jobs. So the specific research questions I want to discuss today for these technologies that I'm showing here is number one, which specific cost categories and technology features drive cost change in low carbon technologies? And there I'm going to look back in time and also look towards the future. And then second, what can we learn from studying past cost changes using mechanistic models, which are models that make explicit how hardware and soft variables and the engineering relationships between them determine different components of costs? How can these models inform future cost reduction strategies? And the method that we used to address these questions involves, as the first step, to formulate technology cost equation, which is essentially an engineering cost model that gives the cost of a technology C at a point in time T as a sum of different cost components, hardware or soft costs in this framework that I'm using today, which are in turn functions of what we call explanatory variables that capture various features of physical component and of the components and of deployment processes. And then in the second step, we derive cost change equations that quantify the contributions of changing variables in the technology cost equation to the change in overall technology cost, either over time or across locations or between two different designs. And then we also use a third step to basically aggregate the result of the second step and think about mechanisms of improvement in terms of the higher order emergent phenomena such as research and development, as well as learning by doing, and how these drive engineering level changes. So what this method produces is essentially a decomposition of cost change into engineering level drivers, as well as higher order processes. And when we apply this method to photovoltaic rooftop systems, let me actually first give you some context about photovoltaic rooftop systems. So this is a technology that has experienced rapid adoption and rapid cost reductions over the past few decades. Rapid cost reductions actually not just among energy technologies, but among technologies in general. Despite this rapid growth, however, photovoltaics currently provides only 3% of global electricity. These are the numbers from 2021, and therefore soft cost reductions are likely needed to support large-scale photovoltaics adoption. So here I'm showing a couple of targets the US government has set for different years for rooftop photovoltaic systems and their installed price. And you can see in 2020, that's the yellow line here, actual costs were quite a bit above the target, and soft costs are one of the contributors to this discrepancy. So one approach to potentially inform future cost reduction is to look over long periods in the past and study the specific cost categories and technology features that drive cost change. Identify avenues that have been successful and potentially pinpoint other avenues that where progress has been lacking. And so when we develop a cost equation for photovoltaic rooftop systems, and when we depict it as a network, it looks like this. So here you can see, I'm not going to actually show you the math because this is somewhat more informative and summarizes it in a more compact and aesthetically pleasing way. You can see the cost components on the left and the features or variables on the right. And the dependencies are shown as lines. So whenever a cost component is a function of a variable, there's a line here. And it looks complicated, but we can summarize this diagram in terms of 3 types of cost dependencies, which by the way applies not only to photovoltaics, but to most technologies. We have hardware costs depending on hardware variables. That's a classic, which I'm going to refer to as hardware dependencies. And then we have soft costs depending on both hardware variables as well as soft variables. So three major technology cost dependencies. Let's briefly look at an example. So mechanical installation costs are a soft cost component that depends on both hardware and soft variables. Of course, it matters how long it takes to install each individual module on the roof. So that's represented here as the soft variable mechanical installation time towards the bottom here marked in red. But then at the same time, mechanical installation costs scale with the area required for a fixed power output, which in turn is a function of the efficiency with which photovoltaic modules convert solar energy into electricity. And that's why you also see dependencies on hardware variables. Zooming in on the soft costs here, which are the topic of this talk, we can see that these are determined by a mixture of hardware and soft variables, but keep in mind that this is a static picture, so we haven't looked yet at how these variables on the right change over time and how much they contribute to cost change overall. And this is what I'm going to do next, and this is the result. So here I'm showing the contribution of changes in all the variables in the photovoltaic system cost equation to the overall cost decline in photovoltaic systems in the US over the period 1980 to 2017. And there are essentially two main takeaways. First of all, you can see a lot of blue in this figure, which represents the contributions of changes or innovations in hardware. And it is, if you think about photovoltaics, which a main ingredient is sand, and then there's that's used to make panels, and then there's a machine called the inverter, which again is a semiconductor machine that converts DC electricity into AC electricity. So it's not perhaps very surprising that 90% of overall cost improvement was caused by innovations in hardware. But when we zoom in here and look at just the contributions from declining soft costs, which are shown in light blue if they stem from changes in hardware variables, and in red if they stem from changes in processes, in soft variables, we see that even for soft costs, the majority, the vast majority, or 3/4, put more quantitatively precise, originated also in hardware variables. So we see these features of physical PV photovoltaics components being decisive not only for hardware costs, but also for soft costs. Whereas in contrast, the contribution of innovations in or changes in processes, changes in soft variables, is very small overall. As I mentioned, the detailed graph was for the US, but we've conducted similar analyses for other major PV markets, including Germany and Japan. The time periods are aligning with data availability, and we find similar results. So this matches with the picture that photovoltaics hardware is exported and used globally, and therefore improvement trends affect many countries at the same time and drive down both hardware and soft costs, whereas soft costs are more of a local issue. So let me use the remaining time to move on to actually two more cases, but I'm going to start with this one, nuclear power plants, a technology that's very different in terms of cost trends. In contrast to photovoltaic systems, we've seen costs increase dramatically, not only in the US, but in several Western countries. And this holds even, as I'm showing here on the right, for plants of standard design. So what that begins to tell us is that either standardization in these plants built in the US wasn't implemented quite as perhaps intended, or it, for some other reason, didn't deliver cost reductions as expected, because even for these standardized designs, cost increased quite dramatically. What it doesn't tell us yet is why, right? So to get at that question a little bit more, we looked at specific cost categories first at the plant level that help explain some of the dramatic cost increase observed in nuclear fission reactors in the US. And we looked at over 60 cost categories. Here I'm showing the most important ones and their contribution to cost increase over the 1976 to 87 period. This period is again chosen based on data availability. And we can see that hardware costs shown in blue also contributed, but over half of this cost increase was in fact caused by various soft cost categories. This includes a category commonly referred to as home office services. So these are activities such as engineering design, managing component purchase, as well as cost estimation. And another category commonly referred to as field job supervision, which includes salaries for various on-site quality checks, as well as worker relocation expenses. Now, this gives us a better sense of what might have been going on with these various soft cost categories being quite influential, but it doesn't yet tell us which specific changes in infrastructure may have contributed to rising costs over time. And to get a bit more at that question while also dealing with the issue that detailed cost data for nuclear power plants as a whole is very difficult to come by, we chose a representative structure, representative for the civil engineering and related cost challenges faced by the nuclear industry. And we developed a detailed cost model for the reactor containment building. And this is what the cost model looks like, again, depicted here as a network. And again, you can see hardware cost components and soft cost components, as well as the 3 types of dependencies I was discussing earlier. And so when we populated this model with data from 1976, 1987, and 2017, again, from the US, this is the result. So again, the bars represent contributions of different changing variables to cost change. Now, in contrast to previous figures, bars extending to the right are showing a contribution to cost increase, okay? And there's, again, a lot going on, but we can break this down into 2 time periods. So in the first time period, the design of the containment building, which again is this large steel and concrete structure that protects the environment from radiation from the reactor in case of an accident, but is also meant to shield the reactor against possible impacts from the environment. During the first period, the design of this building was the same, and the main contributions to the dramatic cost increase actually came from productivity declines. So it became, for some reason, more difficult to deploy steel and concrete, substantially more difficult in the 70s and 80s. And these declines in productivity were the most influential drivers of cost increase. In the second time period, a new design of the reactor containment building was adopted to implement an innovation referred to as passive cooling, which relies on natural air convection, requiring essentially an air gap between the steel liner on the inside, shown in blue here on the right, and the concrete shield building on the outside. And separating these 2 layers in comparison to the one shell design on the left required for both structures to be substantially thicker, so they were able to hold up independently. And so in the second time period, we see these increases in material usage as the most influential drivers of cost increase, but interestingly, not so much by driving hardware costs, material costs themselves. So these are the dark blue parts of the bars, but primarily by increasing the associated labor costs. And this issue was exacerbated by further declines in productivity during the second time period. So what can we learn from this? How can these models of past cost change potentially inform future cost reduction strategies? To answer that question, we populated the containment cost model that I just introduced with improved values, assuming that specific construction innovations have been implemented. So we don't choose a point in time, we just assume that at some point in the future, these innovations may be implemented. And in choosing these specific innovations, we focus on the hardware and soft variables that have proven risky in the past. So this includes both productivity. So there we draw directly on the first time period, and we assume that declining productivity is addressed through the implementation of automated construction systems, making productivity as a soft variable now a feature of hardware, not of a human process anymore, and thus to some degree more controllable. And then for the second scenario, we draw on the information we gathered from the second time period, where increased material usage was the main driver of cost increase. And we assume that advanced and high-strength construction materials are used to replace conventional nuclear concrete, for example. And what we find is that overall, both these scenarios could reduce overnight containment construction costs by about a third, which means that containment buildings would still be more expensive than in the 1970s, but it is a not unsubstantial cost reduction. And interestingly, these cost reductions are delivered, again, primarily through hardware-driven soft cost declines. So these bar charts now show the contributions of all the variables that are assumed to change in these two innovation scenarios to the overall estimated cost decline looking towards the future. And on the left, for the increased productivity scenario, you can see that these formerly red bars, so contributions of soft variables, are now contributions of hardware changes, right? Because, I mean, we're still changing soft costs, but we're now talking about a feature of a robot rather than a feature of a human process. And on the right, we can see that advanced materials interestingly cut costs, again, primarily by reducing labor costs, because you're doing less of a risky process, right? If on-site construction is what is unpredictable in terms of costs and what increases our risk here, then we're trying to make this process a lot shorter by deploying less material overall. Now, before I conclude, let me just discuss two main ideas about electric vehicle chargers, which is to some degree ongoing work, so I don't want to say too much, but if we look at the costs of electric vehicle chargers, in 2019, we also see significant contributions of these non-hardware or soft costs here, primarily concrete labor. So again, a technology where addressing these costs will be critical. Consider that the US, for instance, has announced in April a target of deploying 500,000 chargers over the next few years. So this is yet another critical low carbon technology. And interestingly, again, when we look at different cost reduction scenarios using this model here, the by far biggest cost reductions stem from modifying physical features of the construction site. But here, in contrast to the previous two technologies, we need to be thinking about the combination of local infrastructure as well as the design of the charging station itself. So it matters not only what the station looks like, but also how far it is from the next substation, and so on and so forth. So this is a technology where increasingly we're going to need to expand the system boundary and think about infrastructure conditions to deliver these also hardware-driven soft cost reductions, and use this avenue for cost improvement that has worked so well with other technologies. So in summary, going beyond cost categories by modeling specific innovation mechanisms can lead to counterintuitive findings on the drivers of technology cost improvement. I've shown that both hardware and soft cost declines tend to originate in hardware changes. And these past mechanisms suggest sort of two broad directions for further reducing or for nuclear controlling the costs of these clean energy technologies. The first is to bet on what has worked well in the past, which is to use hardware and reduce both hardware and soft costs through hardware innovation. So for photovoltaics and nuclear, that could mean to increasingly convert soft variables into hardware variables that are less project and site dependent. And as I mentioned, for electric vehicle chargers, this could mean optimizing both station and local infrastructure hardware. And then the other avenue is to focus more explicitly and perhaps in addition to changing hardware, on soft features, on process features. And that also for all technologies that require on-site construction, here we could be thinking, and to some degree, people already are, of course, about high productivity workflow design. So how can you organize the construction site to allow workers to be more productive? And perhaps as a first step to that, what are ways to allow for on-site monitoring of different installation activities to track and really pinpoint what the key inefficiencies are. It's often surprising when you look at this in more detail how coarse-grained the data is that we have on the different cost activities at construction sites and how they relate to cost. So there's a lot of potential for additional research in really understanding what's going on at some of these construction sites and what the inefficiencies are that we want to get rid of. And with that, I'd like to thank my collaborators and our funders, and I look forward to any questions from the audience.
Perfect. Thanks so much, Magdalena and Kerstin, both together. So yeah, I think I'm going to start reading two questions we have from the audience from the chat. So the first goes maybe to Magdalena because we just had to talk. The question is, which one is more environmental friendly? Solar panels installing on houses, building roofs, or using clean energy supplies? I guess the question is for an individual user.
I'm not entirely sure I understand what the second option refers to, using clean.
I guess, you know, just like using the power which comes out of the grid, but like getting a green energy supplier instead of installing a PV on your roof.
So, I mean, in Austria, there is I'm assuming that person is in Austria, there is a substantial contribution of hydropower already in the electricity mix. But if you look at it as a per unit of electricity emissions intensity, the carbon intensity of photovoltaics is still quite a bit lower than the Austrian mix is right now.
Okay. So is there anyone from the audience still who wants to ask a question? So if not, I would have a question for Magdalena. So I was wondering, I guess like one way of like a political selling point for going into green energies is also that it's actually job creating and that it's like beneficial for the economy. And don't you think that, or wouldn't you agree that somehow if you reduce soft costs, and the soft costs are mainly work related, like salaries or like work hours, this is kind of contradicting to fulfilling this function also as a job creator?
Yeah, that's a very good question. I mean, I think at a high level, we ought to be thinking about how we can create demand for these clean energy technologies, and there is going to be higher demand if the prices are lower, right? So this is how markets work at a high level. At a more granular level, I mean, I agree with what you're alluding to, which is that I think we need to be careful, and this is also where I hope that the types of model that I'm helping to develop are helpful. We need to be very careful about which soft costs we want to minimize and ultimately cut to zero, and which we want to preserve for the purpose of jobs creation. So just to give you an example, a cost component that still contributes to photovoltaic system costs is PII, permitting, inspection, and interconnection costs. And here we're talking to some degree about cities, municipalities, and their permitting offices and their staff in these offices checking forms to see if a system has been installed correctly. Now, I would argue that that's not a very interesting and high value job, and that we can do a lot to speed up these installation and permitting timelines, which to some degree is all is already done in different ways in different places around the world. So this is definitely a soft cost where I wouldn't worry too much about reducing it. Also considering that we want to deploy these systems as fast as possible, right? So it's a trade-off between getting rid of some jobs, but then being able to deploy more capacity of this low carbon technology over a certain time period, and being able to meet climate change mitigation targets perhaps more quickly. A different soft cost component where I would be much more careful is construction costs or installation costs. So we don't, especially in developing countries, we want to be very careful about the types of mechanical and electrical installation jobs, which tend to be higher paid often than the average job in these countries, that we are getting rid of. But again, I mean, if we consider automation scenarios where ideally part of, if you imagine a photovoltaics crane or some kind of robot that helps to deploy these systems more effectively and faster, if we're able to develop and manufacture some of these automation technologies in developing countries, I think there is a co-benefit even for jobs creation. But bringing it back to sort of the theme of my talk, which is really looking at these individual hardware and soft mechanisms of changing these costs, I think that these types of models can be useful to avoid precisely, Yuria, what you're getting at.
Okay. And like, I would have like one last question. So, I mean, I've seen and read this about the PV like prices going down so dramatically. And I was wondering if, because you also just talked about, you know, creating demand. I was wondering, is there really, I mean, it's not only the market here which is active, right? Isn't it like a political thing to, you know, why as a, you know, let's say luxury Viennese citizen who anyway thinks, you know, like it's all, you know, hydropower which comes out of the grid, why should I bother putting a PV thing on the roof? It's just a hassle, you know, I have to organize it, I have to pay for it. So do you think it's really the cost which still has to go down for this thing to become even more deployed, or is it mainly maybe a political thing to just push people more into using it?
I mean, I really don't think it's an either or. I think policy-driven investment has been key in creating markets for photovoltaics early on when the technology was too expensive to be adopted without policy support. Now, in many areas around the world, solar PV is actually cost competitive, so it's cheaper than other sources. And therefore it is reasonable for people to adopt it. Does that mean that, you know, we're done policy-wise and we don't need to do anything to support further adoption? No, because electricity sources aren't in many countries necessarily the focus of people's everyday economic decisions. And I think considering that, for instance, sales and marketing costs are a substantial contributor to photovoltaic system soft costs still. There is a lot that cities specifically can do in spreading the word and in motivating people in different areas, perhaps by setting very localized sustainability targets, motivating people to make these choices rather than waiting for solar PV companies to pay for marketing firms. So this would be, for instance, one area where I think urban decision makers have a big role to play.
Okay. So that was it from my side. I think we have no more questions right now. Okay, then I will thank both speakers. It was very interesting again. It was great to have you. And thank you to all the audience for joining us. And